Cool. So then on the moon, what was your max height?
It was 2.3.
And the time you're in the air?
1.71.
Cool. So you have a max height of 2.33 meters. So that's substantially taller, or higher rather, than you can jump on Earth. You jumped 38 centimeters, and now you're jumping 233 centimeters. So this is like the tallest person in our class. Might be James. James, how tall are you? Where's it, Connor? James, stand up. Connor, stand up. Okay, Connor, how tall are you?
6'3".
You're 6'3". Okay, so that would be you on the moon, assuming your initial velocity is the same, you're clearing Connor by probably 3 or 4 inches. It's pretty impressive. On the sun, what do we get?
I don't know. This one doesn't make sense.
Okay, what'd you get?
I got 0.0135.
0.0135 meters. So you're getting barely a centimeter off the surface of the sun. Seems reasonable. I mean, looking at how big this value here is, I mean, even that you're getting a centimeter off is still pretty impressive. VI is 2.73. VF is going to be 0. Your acceleration is negative 275 meters per second squared, and we want D. So if we run that real quick, 2.73 squared VF squared equals VI squared plus 2AD divided by 275 times 2. Yep, I got the same thing you got. So you're barely getting off the surface of the sun. Even that's impressive. It's pretty good. And the time you're in the air? 0.00993 seconds. So it's not even really discernible the amount of time that you're off. This is 9 milliseconds, sorry? 993. So this is basically 1/100th of a second you're off the ground. You're coming back down pretty quick. So this is what I wanted you to go through, giving you guys some idea of the effect of the gravitational field strength from the Earth versus the Moon versus the Sun. Questions, comments, concerns about any of this? Okay. Just a bit of a quick aside here. One of the things that students ask about from time to time is the idea of G-forces. How many of you have heard of a G-force? Okay. A G-force, it's a little bit of a misnomer because it's not actually, well, it is a force, but it's not a force. G-forces are typically caused by objects causing you to accelerate. So when you accelerate, you feel heavier typically, yes? Like you get, if you're in a really fast car, a car that accelerates fairly quickly would be something like a Tesla even, a fairly common car that has a fair bit of get up and go. I sat in my buddy's Tesla and he just floored it. And it felt like I was sucked into my seat, which isn't really what's happening. We haven't. We're going to talk about it today, but the idea of inertia. I think Luis brought it up yesterday. I wasn't sucked into my seat. What actually was happening as the Tesla took off?
You were sitting at 0 and the car was accelerating before you were at the same acceleration rate.
Right. So the car is actually like enveloping me, trying to push me forward, which is as I'm trying to lean off the seat continues to push me forward, which is why it feels difficult to move. This happens in, another classic example would be something like a jet fighter. I have never had the pleasure of riding in a jet or roller coasters. All of these things provide G-forces to you. G's are just multiples of this acceleration due to gravity here. So you are all right now experiencing, well, if you were to we were to push you off a building, you would experience 1g, the acceleration of gravity here on the surface of Earth. So if a car is accelerated 4.9 meters per second, how many g's are you experiencing there? 1g is 9.8 meters per second squared. Sorry? Half a g. Because this acceleration is half of Earth's acceleration. So it's going to be 0.5 g's. Back when we had a space shuttle, the space shuttle, as it was lifting off, would accelerate at 28 meters per second squared. How many g's are going to be experienced by that astronaut as approximately 3? How'd you do it? Oh, 3. Oh, so 9. Okay, but it's not 9, it's 9.8. So what is it exactly? What are we doing? Yeah, you take the number of the acceleration that we have and divide it by the acceleration of, or due to gravity, sorry? 2.8 what? No, 2.8 what? What's the next digit? So we want to round it. We just don't want to just cut it off. 2.86. So yeah, almost 3. And fun fact, a normal human can withstand about 4 Gs before passing out. But you can train your body to tolerate more. A fighter pilot can typically withstand up to 9 Gs. The aircraft itself can actually handle around 11. So there's...
Don't they have like suits that like keep your blood running so you don't pass out though?
But even then, 9 is what? Yes, it's part. Yeah, part of it's the training, part of it's the suit, the compression suit. So, what's the acceleration there? It's cheating a little bit. Sure, we'll allow the fighter pilots to cheat. What kind of acceleration would cause you to pass out? No, it says 4 Gs. We're assuming you're all normal people. What acceleration?
39.2.
39.2. So you take your 4 Gs times 9.8 meters per second squared. You said that was 30. Sorry, how many?
39.2.
39.2 meters per second squared. And the fighter pilot's going to withstand how many? Or how much, rather, acceleration?
Hold up. 88.29.
Cool. So then the question is, what's actually causing you to pass out here due to these accelerations? Well, what is it? Oh, your blood's moving still.
I think it just goes away from your head though.
What do you mean?
Well,
What causes your blood to leave your head?
the V-force, it pulls your blood.
Is that what's happening?
I have no idea.
It's a good guess.
The whole blood of the brain coming like to one part, so the other part of the brain is bloodless. Like there's less blood than needed, and then you pass out.
But why?
Because blood needs to circulate around all your brain to the brain side.
Yeah, but so that part I understand. Yes, your brain needs blood to keep you conscious. But where's the blood going? How is the blood going there? Sorry, I don't care about where so much as how. How is the blood leaving your brain? Typically, it doesn't do that. Manuel.
If you look at blood as an object, it wants to stay at rest. So then if your body keeps moving forward, your blood stays the same spot.
Your blood wants to keep doing. Is it just rest?
Well, it wants to continue the motion that's currently going on.
It wants to continue in the motion that it's currently going on. Okay.
Yeah, and so similar to how we are in the car, but
It's gotta be
our
like
body
really
moving in what state.
So as you move, or so what you're telling me is, as you move around your blood, the blood stays static, and you move around it, causing it to leave your brain. This is what I'm hearing you say. That's not what you said? Or that's not true?
Maybe I didn't understand you.
Your blood, what I heard you say, Manuel, is that, so like me sitting right here, my blood is where my blood is. It's located wherever it is in the veins that are on my body. If I were to undergo this acceleration very quickly, what I heard you say is that my blood wants to stay where it is while my body moves around it in a different direction.
No, it's say
And then my blood takes a little while to catch up.
yeah. And that's like if the blood that's in your like prefrontal cortex would go back to your
Assuming that I'm moving which direction?
okay.
So if I accelerate forwards, the blood that's where it is just going to stay there, and I'm just going to move. The rest of me moves that way, and it takes a little while for the blood inside of me to catch up.
That is what I want to say.
That's what you want to say.
That's what I want
That's correct. That is completely correct. That's what's happening. And you don't notice this effect because you guys don't typically ever experience accelerations like this. Or you're losing consciousness for a different reason. Let's look up what you experience.
Like a roller coaster can get,
to get past it, but
you know, like approximately how many G's a roller coaster has.
legal amount of roller
There is some people that's out in roller coasters.
probably
Actually, Manuel, this is interesting. A rugby player can experience an impact with an average of 21 G forces
What? From what?
from other people.
Like how?
Well, Manuel can explain to you rugby later. But yeah, so
shoulder, ribs.
how many G's in a rugby tackle?
There's a football. I think football is higher.
20. Football is higher, 63. Which is why football helmets are a thing, which is why padding is a thing. The difference here, though, fundamentally, is that not necessarily all of you is experiencing the same G-force. It's not causing your blood to shift the same way that a fighter pilot would experience that, because the fighter pilot's entire body is accelerating with these G-forces, where only parts of you are accelerating with those G-forces, and it's not as long. It's not as sustained. So there are some. When you think about when I give you this number, 9 G's is going to cause you to pass out. But Manuel, who's playing rugby, regularly experiences 21 G forces, and he doesn't pass out while playing. Well, what's going on there? It's not your whole body. It's not sustained.
I think it's the
The time that is staying in that speed, like for example, pilot needs to like he won't stop when he reaches his speed, so he needs to stay in that speed for a long time. So that's why it's different, because in the rugby, I think that is just for a instant moment.
It's very short. Yeah. Yeah. So let's flip the page here, because now that leads us into this discussion here on inertia. This is Newton's. We haven't even talked about Newton's first law. We just introduced to you guys the idea of forces. We talked about accelerations. Newton's first law, he came up with 3 of them. The first law says this: an object in motion is going to do what? Does anyone know?
Stay in motion.
It's going to stay in motion. And an object at rest is going to stay at rest. Unless what happens to it?
Unless there's applied motion.
No.
Unless there's applied force on it.
Unless it's not necessarily an applied force, because you have gravity's acting on you guys right now, but you're all at rest. But what else is acting on you? So Luis, you said yesterday you're sitting in the chair, gravity's pulling you down, the chair is pushing you back up. So you have forces acting on you, but you're at rest. So an object in motion stays in motion, an object at rest stays at rest unless what? But you have forces acting on you right now, is the argument I'm trying to make. So it can't be that unless a force acts on you. It has to be
The force is
Not necessarily.
Bigger than weight.
Nope. You don't think about just the single situation that you're in now. Because the sentence that we write down here has to be true for all objects in all situations. It's not just about lifting you up out of your chair or throwing you down into the ground. What has to be true for an object? Well, sorry, I shouldn't say it that way. An object's going to stay in motion. An object in motion stays that way. An object at rest stays that way unless what?
The force is greater than the friction, I don't know.
Again, you're being too. You're getting the right idea, Luis, but you're being too specific. Because friction, yeah, that's one specific example. Gravity, well, that's one specific example. But how are those situations related?
That's quite hard. It's too general.
But that's what we need. We need a general statement that is true for all of these situations together. Yep, you Googled it.
No,
What'd you
I
get?
didn't, I promise. Unless acted on by a force. I 100% did not look it up.
But it's not a force, because forces are acting on you right now. What kind of force?
Self said it.
Sorry?
A significant force?
When the force is bigger than I
Did you Google that?
No, I didn't.
No, Canwar. You're right. Unless acted on by an unbalanced force, or the way Newton said, he said a net force.
What do you mean in net force?
Okay, so like a net. So the way he said it, a net force is when you add up all of your forces, which we're going to do. You get a value that's not zero. For example, the force of gravity acting on you is pulling you down. The chair is holding you up. Because you're not moving, those two forces must be balanced. So the net force acting on you is zero. But if I tell Manuel to grab you by your left shoulder and push you really hard to the side, what's going to happen to you?
Stay right here.
Manuel, do it. Okay, what happened to Connor?
Stay there.
He moved. Why did he move?
Because that was an unbalanced force.
Because Manuel was providing an unbalanced, or the way Newton applied it, a net force. But what if I told Manuel and Naya to push on opposite shoulders?
Balance. Plus,
Are you going to move?
Depends on how.
Okay, now Naya, put your hand on Connor's right shoulder if you don't mind. Manuel, I want you to put and I want you both to push. See, there's forces acting on you now that way. Push hard, Naya. Manuel, push hard. Okay, is Connor moving generally?
yes.
Well, look at him now.
Staying in the middle. Which is
He's still staying in the middle, right? He's not moving. Okay, you can stop. Thank you.
Thank you.
So in this second situation, was there a net force acting on Connor, or was there an unbalanced force acting on Connor?
No, because there's two like equivalent forces on both sides.
Right, because the force provided by Naya, thank you, and the force provided by Manuel, thank you, balanced each other out. Connor, you experienced forces. Yes, you could feel them pushing on you, but did you go anywhere?
Yes. Well, no.
When they were doing it properly, did you go anywhere? No.
No.
Thank you. Okay? So this is also referred to as the law of inertia. Inertia is defined as this: the tendency. Is it A-N? No, it's E-N. Dang, I always get that wrong. Tendency for an object. Nope. It's close. To keep doing what it's doing. I'm just being more general. It's related to momentum, absolutely. We're not going to talk about momentum in Physics 11. Momentum is going to be a topic you talk about in Physics 12. But it's related to these ideas of inertia. What is the largest, or what are the two, I guess there's two. What are the two concepts related to how well an object can continue to do what it's going to do?
Resistance. Or friction.
It's not friction.
Can you repeat the question?
What are the two, well, let's say it a little differently. What are the two aspects of an object that will allow it to continue to do what it's doing?
Weight can be.
Sorry?
Weight.
You're using that word. We don't like, it's mass. Mass is the big one.
Like I use weight because like the acceleration of gravity applied to the mass is the weight.
Yes, but mass is the thing we care more about. I don't want you to confuse those two. Mass is the thing. If Manuel was running at you at 10 meters per second, or if Mr. Fujimara was running at you at 10 meters per second, which one of them is going to be easier to change their motion? Which is going to be easier to change, i.e. stop? No. Who's going to be easier to stop? If Fuj and Manuel are running at you at the same speed, which one do you have a better chance of stopping?
No, at the same speed.
At the same speed.
Oh.
You and Manuel, you and Fuji are running at Connor at the same speed. Which of you does Connor have a better chance of stopping? You. Why? Because there's less mass, right? So inertia is completely impacted by your mass. Objects with large masses have a lot of inertia, even if they're not moving very quickly. So let's say Fuji is just walking at you, and Manuel is just walking at you. Manuel, you could stop pretty easy, but if Fuji wants to keep walking, Fuji is going to keep walking. Okay? What's the other thing that impacts inertia?
Format of the thing, like
The velocity. Velocity is also a piece of inertia.
like the format of the object is included on mass, I think.
When you say the format, what do you mean? Like the shape?
At the same time.
Shape is, it's less about shape. It's more about how much of the object there is. So, but mass and velocity are the two key points here. So we compared different masses, Manuel and Fuji. Now let's compare Manuel with Manuel. If Manuel is walking at you versus Manuel sprinting at you, which version of Manuel is easier to stop? The walking. So objects with lower velocity and low mass are going to have the least amount of inertia. High mass is going to give you a lot of inertia. High velocity is also going to give you a lot of inertia. So for example, if I tossed something with low mass, this ball of sticky tack, if I just kind of lobbed it at you, that'd be really easy to stop, yes? What if I shaped into a bullet, froze it, and shot it out of a gun? Same amount of mass,
It would probably like break in the chamber.
but it would either break in the chamber or it would punch right through you.
I don't like that thought.
It's a terrible thought, right? So even objects with low mass, if you give them enough velocity, become difficult to stop as well. So inertia, the tendency of an object to keep doing what it's doing, this is Newton's first law. So let's imagine here you are racing around a track on a go-kart. How many of you have go-karted before? Hands up. If you've never go-karted, think about the last time you drove faster than you should have in a car. When are the times where you notice inertia being a thing? When you're turning is one, okay? Turning is one. Speeding up is another. And slowing down is the third. Okay? Those are the three times you typically notice inertia. What is happening in all three of these times? It's a change of, be more specific. Change of, I heard it, someone said it, velocity. These two, speeding up and slowing down, changing velocity makes sense. But how is turning a changing velocity?
Slow down because your velocity is sustained.
Well, let's assume you don't slow down to make the corner.
When you turn the car, slow down a little bit.
Well, let's assume it doesn't.
Or you go straight.
It doesn't have to.
Your velocity. No,
Sorry, Zaid, keep going.
you're turning, so you have a different direction of velocity.
The direction is what's changing. Velocity is a vector, and vectors are made up of magnitudes and directions. If you change either one of those things, you're changing the vector. And when we change velocity, what are we causing? No, that's only assuming we're in a circle. Changing velocity is caused by, or no, changing velocity we call starts with an acceleration. So the act of turning is also an act of acceleration, because while your overall velocity might not change, you are let's say I turn right. You have to turn right, you have to decrease forward velocity and increase velocity to the right, yeah? So those things kind of happen at the same time to be able to make that corner. So in a sense, you're right. You're slowing down in one way direction and speeding up in another. So that's causing an acceleration. Accelerations are what, or whenever you're accelerating, that's when we notice the inertia. Another way to think of Newton's first law is that if there is no net force on an object, so if F net equals 0, then your object's going to stay at constant velocity. And if your object is already not moving, that constant velocity is 0. Objects that are at rest are also at constant velocity. It just happens to be constant no velocity, 0 velocity. So imagine a book sitting on a table, or you sitting in your chair. The force of gravity pulls you down, or pulls the book down. We know this. But there's also a supporting force pushing up on the book. We call this supporting force, we call it a normal force. Does anyone know why? No, that's a good thought. But again, normal has other meanings in other contexts. You guys hear normal, you think, oh yeah, it's usual, it's around all the time. That's not what normal is defined to be in this context. Luis.
Normal, would be like the force that the book's applying on the table, and the table is applying on the book, the same, so that's normal force.
Normal force is just one of those, not both of them.
Oh, the force.
Normal is just the one that the table applies to the book.
Okay.
So let's draw what Luis just said. We've got a table, which is why we've got space down here. Luis, you're really good at guiding us further to exactly where I want us to go. And I appreciate that. So there's our table. Here's the book. What forces are acting on the book? Gravity is one. So from the center of the book, I'm just going to draw an arrow down because we haven't talked about it yet, but forces are vectors. Forces act in a particular direction. And gravity, we're just going to call Fg, the force of gravity on the book. Gravity always acts straight down. And what other force is acting on the book? It's not moving, so there has to be another one.
Normal force.
The normal force is which one?
Resistance force.
It's the force acting from what object onto the book?
Table.
The table onto the book. And because my book is not moving in any direction, the normal force has to be which way? Straight up. And normal force we typically write as F capital N. That is my normal force. I think someone, no one said it. Normal in a mathematical context, this word here means perpendicular. Yes. What does perpendicular mean? What does that word mean? That's parallel. What's perpendicular mean? No.
Something vertical crossing a horizontal plane.
Yes, but what is? How do you know they're perfectly perpendicular?
Because they have a 90-degree angle.
There's a 90-degree angle.
I don't see no 90 degree there.
Okay. Okay. So a normal force is always perpendicular. Running out of space, so I'm just going to float over there. Always perpendicular to the surface. Always. And gravity always acts which way? Straight down. For another example, I will. It's coming. I have not forgotten. If I drop a book from 2 meters, the only force acting on it is gravity. Because that object is no longer sitting on the shelf, there is no normal force acting on it, the book is going to start to what? Accelerate. So let's draw it. The only force acting on that object is gravity once I let it go. So that's going to cause this thing to...
And when it reaches the ground, like the instant impact would be like a bigger normal force because like there's acceleration on it. So, for example, if you drop a fruit, for example, the fruit can like have receive damage because the normal force and the moment that touches the ground bigger, then it stays still.
Yeah, the normal force has to bring it to a stop. So, yeah, I mean, you bring a good point. The normal force is always going to... It's a force between a surface and an object that causes the... This is a supportive force. So, I mean, let's talk about what you said there. Instead of a piece of fruit, I'm just going to leave my calculator here. In this case, because Luis brought it up, we'll talk about it. The normal force on my calculator is going to be equal to what? No, that's an acceleration. What's the force on my calculator going to be? It's going to be equal to gravity, right? Because this, right now, the only force acting on my calculator is gravity pulling it down, whatever Fg is. We remember how to calculate mg? Oh, sorry, hang on, I gave it away. To calculate the force of gravity, we take the mass of my calculator, we multiply by g, right? We talked about this yesterday, Fg equals mg. So that Fn in this case, my normal force, the force from the table upwards on my calculator, is going to be equal to gravity. And we know this because the only force acting on my calculator is down, but the calculator is not moving. What happens if I do this? The normal force has to increase. Why?
Because you're applying more force, so the Newton law says that force needs to be equal, like any force, any action has a reaction, so
We'll get there.
reaction
Don't
of
use that one yet, but you're right. The point for this law, has my calculator started moving even though I'm pushing down on it pretty hard?
no.
No. So that there has to be a balance to all of the forces because this thing is continuing to not move. So you're right, Luis, Fn has to be increasing. It was what it was to compensate for gravity, but now it also has to compensate for me pushing down on it. So Fn doesn't always just balance Fg, it also balances if the thing's not moving. It also balances whatever other forces might be pushing on this object. Yeah.
But isn't it just the resistance of another object, not necessarily a force?
But the resistance is a force.
Right.
And I'm not going to use the word resistive because it's not necessarily resistive, but I like this word here. Like, it's a supportive force. It holds things up. You can't have, like, the wall, for example, isn't necessarily going to have a normal force on my calculator because as soon as I let go of the calculator, the gravity is just going to cause it to drop. So resistive isn't necessarily the word. When we'll talk about resistive force later, a great example of a resistive force would be something like friction, something that opposes you doing something else. Fn just exists to support things. More examples for inertia here. Riding a skateboard or a scooter, unicycle, bicycle, whatever, you hit a curb. What happens to you?
You start falling.
You keep moving forward.
Nothing's supporting you up that. Your foot can support you.
You continue, but in the instant you hit the curb, don't think too far ahead. The instant you hit the curb, you continue forward, and the object that you were riding does what?
Stops instantaneously.
It's not quite instantaneous, but it might as well be. The object you're riding stops. Why does the object stop? It experienced a, it's not the normal force, it's whatever force the curb applies. So the curb has applied a force, so the object stops. You haven't experienced a force on a skateboard, a scooter, or a unicycle because there's nothing in front of you to provide a force on you. So you keep going. If you're sitting in the back seat of a car and it makes a hard right turn, what do you experience? Sorry? Practically, what happens to you? Like, let's draw, okay, fine, we'll draw the picture. From the top down, here's the car. You're in the back seat. Let's put your head right there. The car does this.
Oh, you hit the window.
What do you experience? If it happens quickly enough,
Would be like instant acceleration to another direction, so that makes your body turn to the direction.
what's the first thing that you experience initially? Sorry? Not necessarily. Like the car is moving. I am the car. We're just moving along. You don't necessarily feel anything because I'm going at a constant velocity. And then I turn right. What do you feel? What happens? Sorry, no, don't let you. What happens to you practically?
Body wants to keep going the direction it's going before, so when it
Even more practical. No. Like, what do you experience? Like the first thing.
your shoulder,
You're sitting in the car. What do you feel?
seat buckle.
No, that is a seat buckle. Seat belt?
Do we have to go to my car?
Yes.
Do we have to go to my car and make a hard right-hand turn? Can't do that with all 30 of you.
Just one at a time, with gas prices like this.
What do you experience? What happens to you in the car?
Your shoulder hits the door.
Your shoulder hits the door. Okay. Why? There's not an acceleration forward. You're just moving. Okay. The reason for that is because you want to continue forward.
But inertia makes makes your body want to continue to go to the same direction, but when another acceleration is applied on you, like another force, you want to keep moving in the same direction, so that's why your body goes the opposite way.
Your body does not go the opposite way.
Nope.
your body continues the way your body was already going. You don't go the opposite way. You keep going the way you were going before. You're going to keep doing what you were doing, but the car around you has changed. The car is now making the corner. So it's the fact that you wanted to continue going forward, and the car says, no, we're turning around you, doesn't throw you into the side of the car. It throws the side of the car into you, because it puts itself in your path. It's exactly the opposite of the way we think about it. Nothing's happening to you. You were just minding your own business, traveling through the universe. And the side of the car got in your way. Now you have a bruise. The effect is the same. You hit the side of the car, but the reason is completely different. And it's the understanding of what's actually happening in the universe that makes this course so difficult. Because you think you have an understanding, and practically the reason I'm giving you and your understanding, the results are exactly the same. But you've got to reframe your thinking to address what's actually going on around you.
You gotta show us the ways to the course to figure out.
I'm working on it. Headrest, number 3 here. Headrests are placed in cars to prevent whiplash injuries during rear end collisions. How does this work? Has anyone here been rear-ended? How is that? That's a good experience, yes? Was yours pretty quick? Were they moving pretty fast, or was it pretty slow?
He was slowing down in the rear of it, like,
And he hit you. Same kind of situation? And yours was pretty slow? Okay. What's the headrests? How do they prevent whiplash? Those of you who have experienced being rear-ended. What part of you goes forward? So let's draw this on again. So here's you. Let's say you're driving. You're sitting in your seat in your boxcar. You're not moving. And then you get plowed from behind by this little green sports car. What happens to you? Let's think about this piece by piece. Green car hits you in the blue car. What does your car want to do? Well, what is your car going to do? The car is going to go forward. But all of these things, you aren't the car. You're not built into the frame. So there's going to be a bit of a delay between the car moving forward and you moving forward. And which part of you is going to move forward first? Everything that has support. So if the headrest doesn't exist, the only part of you that's being pushed forward is whatever part of you is touching the seat. So the seat's going to move into you. If there's no headrest, it's just going to be your shoulders, your back, your butt, probably the back of your knees. That's going to push you forward, assuming there's no headrest. And your head is going to want to do what? It's going to want to stay. All of a sudden, you get whipped back, and now you have whiplash. So the existence of the headrest is to keep your head with the rest of your body as you move forward. So it moves your head with the rest of you. Because your neck's actually a fairly weak, it's one of the weakest parts of your body. Does anyone know how much force it takes to break a neck? You should know, lifeguard.
I shouldn't know. I'm just supposed to put them in a spinal plan.
You don't know the value?
No, I'm just supposed to put them in a spinal plan.
Okay.
Probably like 20.
No, it's pretty small.
And so then they had to.
It's actually only about 16 newtons.
I was not far off.
You were close. And 16 newtons, you can provide, so it's about 4 pounds, which is pressure that you can apply with just your thumbs. You can break a human neck with just your thumbs, assuming they're not resisting you. Obviously, if you walked up to someone and said, I'm going to break your neck with my thumbs, they're going to tense up. But if you manage to catch them sleeping,
Bro.
and you are more than strong enough to snap their neck with just your thumbs. Okay?
Like this or like this?
Like pushing down.
Alright.
Okay? So the neck is actually fairly weak, which is why whiplash is such a big deal. Because it doesn't take much for the rest of your body to slide forward and your head to remain where it was. Because your head actually it's fairly heavy. Your head weighs about 10 pounds. The brain itself is about 4 pounds. So the skull and all the other tissue brings it about 10 pounds for your head. It wants to remain where it is, but if the rest of your body just slides forward, now you've got your neck snapping back, causing whiplash. That is the purpose of the headrest. Not just to be awesome while you sleep in the car, but to actually potentially save your life if you get rear-ended hard enough. So that's how inertia impacts this kind of stuff. Questions? So if you can see in the rear of your mirror that someone's not stopping and they're going to hit you, just tuck your no, you're already not moving. Just tuck yourself back into your seat as far as you can so that you can move with the car.
Like go lower?
No, just like push yourself back into your seat. Like lean back into the headrest and just hold yourself. Relax as much as you can and let the seat just carry you forward. And that will do the least amount of damage to you.
Prepare to yell at the person.
And then deal with all of that later, yeah. Okay, I want you to flip the page. I messed up the photocopying, so I want you to flip 2 pages forward, and I want you to flip to this one here. Oh, there's lots of time, yeah. We're going to do 2. The first, I want to give you some time to work through this. It's just conceptual inertia. Like, there's not a lot of, there is no calculation here. It's just ideas surrounding inertia. The calculations will come when we talk about Newton's second law, which we're going to get to today, because there's still like an hour and 15 minutes left in class. But I do want to give you some time to look at these. Actually, I lied. There's a few calculations, but they go back to the weight stuff we were talking about yesterday. I want to give you some time. We'll give you about 20 minutes. We'll see where you are in 20 minutes to work through these 7 questions. At the end of, well, I'll check in with you in 15, but 20 minutes I figure you should be able to get through this, and then we'll move forward. I'll be moving around answering questions on all of this, but if there are no questions to start, I want you to work through these 7 questions. Feel free to work with the people around you. Yeah, I was not, I knew what the question was. Giver. Okay. If you are done this page, what I want you to do is flip back to this page, and you're going to need either a computer of your own or grab one from the card at the back. You're going to hop into Google and you're going to look up FET forces and motion basics. And you're going to run this thing. These questions are going to walk you through.
Can you give me malware or something?
Yeah, you're going to get viruses. Lots of all the viruses. No, this is software created from the FET stands for, I think it's Physics and Engineering Technology. It's the PhD physics department out of the University of Boulder, Colorado, has created a whole bunch of these. They used to be Java applets or Flash applets, but because Flash is no longer supported.
FetColorado.edu.
Yeah, that. They're educational physics resources. FET forces and motion basics. See, I can show you up here too. So let's do that. Let's do that. Oh, my computer is slow. No, I don't want that. Whoops. Don't do that. This is how my computer crashes.
Oh, Netflix. Oh. Bro, what am I doing?
Okay, I want you to search FET forces and motion basics. You're going to click on. Okay, guys, stop talking, please. You're going to click on this one. My computer's real slow because I'm doing a lot on it right now. You're going to click play. It's going to open up the simulation and you're going to go through it. I think the questions, I'm hoping I made them sufficient that it's, there's not a lot of questions there for you to, figure out how to go about what I want you to go about. And it's going to lead us into the next lesson. So only jump to that if you've managed to work your way through all of this. Inertia worksheet 1. Finish this and then move back a page and take a look at the forces and motion basics. If you have to grab a computer at the back, grab a computer at the back. And you know what? Let's do that, and we'll talk about all of this to start class tomorrow. We'll take this up. And we'll talk about how this has gone. So I guess we'll call that your homework then. Let's say that's what's going to happen. I don't know what that noise is, but please stop. Inertia worksheet 1 and forces and motion basics. This is what I want you to work through now. And that'll be the rest of the class. But make sure the inertia stuff's finished first. Sorry? 11:25.
What do you mean the vector arrow?
Oh, that makes so much more sense.
Sorry?
What do you mean the?
Okay, what do the instructions say?
First scenario on the roll pool in which the forces are balanced.
Okay.
Balanced.
Yeah, I know the
Because they some forces zero and turn against.
And these are what?
That is or
No, what shape is this? That is a vector arrow. You're asking me about vector arrows. They're there.
So you want us to draw this?
Yep. Yep. Yes. That just goes back to what we did way back here. Not way back here. Yep. Here. What do they do? Yeah.
So are we multiplying it by 9?
To find the weight on Earth, yes. You take the mass and you multiply by 9.8.
Okay.
Yo, these guys have a long choices.
Question 3, you were in a spaceship and fire a cannonball in frictional space. How much force you would exert to keep the ball keep going? 0, I think.
Look at this.
It's true.
Look how long the force of that
This
is.
is- I was trying to overcomplicate it.
Alright.